Okay, hello everyone. Today I'm going to talk about the sandy sand, but in tri-social space. In the next episode, I will talk about sandy sand in multi-axial space. So for first, we should take a look to the key concept of sandy sand model and its practicability. So you can see the second picture over there from the figure 1.1. You can see the dilatancy, critical power, and the bounding. Okay, and this is the yield surface. You can see there. You can see the eta. Eta is the equal of the derivative stress on the pressure, and the next is alpha. Remember 2K because this constitutive model can uh, capture the complex cyclic liquefaction behavior. Okay, so if you know about the Simpson, this is the sandy sand is more complex, and it's actually work by the same way. Okay, so we have the MP, the MB. MB is about B is bounding or peak. Mm, D is dilatance, or PT is phase transformation, and M is CXL, critical state line. Okay, and you can see the picture there. I draw six figure in one. The first is PE, and the second is P log P E log P. The next is step. You can see there is lot and lot, lot and lot, lot and lot, lot and lot. And next in there is axial strain and shear stress. You can see there it's so really complicated because it touch cyclic. Okay, and the final is P and Q. In there it's a really special figure. This special figure is about fabric. I will tell you in the end of this video. So I think I just take a quick all of this and focus on there. We have the elastic property, yield function, ballistic potential function, loading reversal, and fabric evolution. It's all I will talk about in this episode. So, as you may know, we have the epsilon VE is dp on K, and epsilon QE is dq on 3G. And we have the dilatancy rule D equal d epsilon VP on d epsilon QP. And we have more thing to learn. Is there d epsilon QP equal d eta on H is Hunting modulus. Okay, we will talk is and remember the epsilon VB is very important in unloading process because on a loading process we can call it loading reversal, and all of the sign change, so make sure you have to change the epsilon VB because when we loading how we just change the dg on dp. Okay, because d lambda is negative at that time. I will tell you why. Okay, maybe I have to tell you this now. Okay, when we had a cyclic happen, something happen is there. Why we have to make sure the epsilon VP positive? We have d lambda is always f trial on 8e plus 8p, the sum of them. You can see there when we have the reversal in the f formulation, is the yield surface formulation, yield function. You had the sign like this, the sign change, and QE alpha pi become to lower than zero. So if trial is negative, it's negative, and this make d lambda is negative. When I try to run the MATLAB code, I search on I just saw on of the value, and I just decided I just see the lambda is negative when we in a loading process. So to make sure the epsilon VP positive in the reversal loading, we have to change degree and dp at a time. Okay, I'll show you in the code. The code is there. It's only in during reversal. You have to make sure to change it to negative, okay? Because d lambda will be negative. It's just really total different. It just total strange. You know, we had f. F is always lower than zero or negative. We can call it negative, and it's on elastic. When if equals zero and it's in plastic, electroplastic stage, and d lambda is totally the same. D lambda equals zero when elastic, and d lambda is more than zero. Is you can call it positive. It's always two. It's never lower than zero. So we have to change it, or we have to understand it because it reversal. So d lambda is negative during the reversal. We can get familiar with it, but we have to change the epsilon VP to positive. So that's why we do it. Okay. Okay. Then the next time I'll show you this elastic property. We have this from Richard et al. 1970 with J0PAT 2.97 and K to 1 plus Poisson ratio. Okay. It's really special. I will show you the Simpson. With the Simpson, we had a QP minus MP epsilon QP like that. It's the Simpson model. The Simpson model told that when epsilon QP change, the QP will move to MP when the epsilon QP to infinity, and it just make QP equal MP, and it's moved to MP. But it can't to out capture cyclic. So with the new function of the descent, you can see that we have the APX of eta minus alpha and m. So you can write in the other way like that by multiplier from eta equal q on p. So you can have the new equation like that. I always use this equation, okay? But you can use anything if you want. In my model, I know in my code I use this. So what the alpha and QP, you can see there it look like they were a trick because it just depend on epsilon QP. So we have this at that time, and alpha y alpha is epsilon QP. So you have to solve all the formulation there, and finally you can have this equation. It just really alpha depend on epsilon QP. So whether this is the same or not, everything every time it change, you can see that it will grow up and just talk to the MP. So this descent is just totally same with the Simpson. Can catch, and the loading surface will move forward to the MP and stop there. Okay, and MP will move to the critical state line and stop at that time. Okay, I will talk a bit more clearly in the end of the video. Okay, so we have the use surface. It's hardening mechanism like that. I want to talk one special thing is that when we in the load, I call it load stage, and the load stage, load can call compressions, shear, and a low E tension shear. Okay, so with the low stage, we can use alpha and eta on there, but when a low, we still use alpha, but eta change to there. Okay, it's different. maybe the alpha move. We had alpha. Eta is just fixed, okay? Eta and alpha like that. I'll show you. So Sandisen just have the same of the limitation of the rhetoric capturing isotropic hardening mechanism, could predict hardening response elastic. So we never have the elastic stage of the isotropic hardening mechanism. Okay. I'll make it quick and focus on explain the fabric. So you can see the hardening rule there, D alpha, MP, and eta. Okay. It's just a distance, MP minus eta. And you can see eta will increase, and when it's at the peak of state, and one special thing you can see there, we have the MP and MD, it look like Simpson, but we have more parameter is C0. Parameter controlling rate to beating, bounding, and dilation, straight rate to compression in pseudo intention. 0, 1 for isotropic hardening material. So we had a load, we use C0 equal 1, but a load we have to use the new C0. Okay? And especially there's that M, it actually changed CL. You have to use C0 for the M2. Okay? So we have the load and unload like that. Wait, I'll show you. To take a picture there. Take a quick. You can see there, this is the CL, but this is the CL with the C0, okay? This all of load and unload process, and I'll explain more clearly to you at the end of this video, okay? It's done. It took me 10 days to make the animation of cycling, but I think it's really okay because I understand it all. So the next I'll talk with you is plastic potential function. It's really actually the same with Simpson. It's use dilatancy rule, and assuming there's a plastic potential function. With the dilatancy rule, we have used D like that, and definitely as in Manzuri 2004. So we have the derivation dr on dp and dr on dq like that. That is the zero, meaning avoid an explicit definition of the plastic potential function. So we still have consistent condition, but it actually look like Simpson. Strength control like that, and strength control like this. Okay. This is the U function I just listed above, and I try to derivation is like that. I use this function and derivation df on dp. So we have this, and df on dq. We have this df on dn far. And actually I copy the dn far and derivation it to make sure we understand it all in the future. Okay, we have all the potential function, but it will change because we have the loading reversal. The important thing in loading reversal is that you have to understand the cyclic loading is complete liquefaction. The d eta also changes its direction. You have to focus on it. When it changes direction, it means in cyclical loading. It just really make we confused with the terrain triangle, but we just focus on terrain now. Okay. So when we have the eta positive, it's mean compression. It just increase, okay, like that.
The elephant drinks the milk.
It's increase like that, increase, just increase. Delta increase, you can see this move forward to the CLR above. And when delta is 0, it's moved tall forward to the end, okay, to below. So when delta reduce.
The elephant drinks the milk.
Even minutes make it tension here and it's above it compression here. I take a note there. Compression here, okay, and tension here. Okay, you can look picture there. I continue. The specific treatment, this change in sign of the stress increment rate would result negative plastic strain increment. The physical incorrect. So we have to focus on there. This means the epsilon p. This means the epsilon p. Okay. So when we unload it, loading reversal, it make us have negative plastic strain increment. I just explained you from the first beginning of the video. We have the d lambda is negative. It's never negative in the past in the other model, but it's loading reversal. It f change. F is lower than 0. So it make d lambda is negative and the d lambda negative. So we need, for the first time of this, we need this on VB is positive. So that's why we have to change the derivation of the DC on dp. Okay, so there. Furthermore, the loading reversal curve, this there no longer is exist. The concept of distance will be no mph no longer exists. Another bounding surface in extension regions. So we have to focus on the distance. You can see there for the first time you can see this work like that. We have the MP is the red line, dash line, okay, and we have the eta line like that with cyan color, and the distance meaning the distance like that from the angle of the MP and angle of the eta. So at the first time we can use MP and eta like that, but when it changed you can use this formulation anymore. The eta is loading is totally different and the MP of Earth is fixed. You can see it when MP is negative, but our MPMD is fixed. It's always positive. So that we have to change this. And when we change it, it means the MP is the eta is changed over there. So make sure it keep a distance. So when loading, you just change this and fix this value. So 50 is always positive, and it means we have D and far. We're good. It's good. Okay, we just keep it a distance. Okay.
Is the spider under the cheese?
It's always a distance. If you know when loading reversal, we have to change it from minus to positive. It's always a distance. D and phi is equal to 0 when you stop, or MB eta division PP 8 with a one more value, so that it make alpha move toward there. Okay. With the next, the same time apply for dynamic reversal loading. We still change all of the MP or MD minus eta 2 plus. It just keep it always a distance. Okay. The eta now is negative value.
Elephants live
When
in
we
Asia
use
and
it, and
Africa.
MB over there, it's to keep it
Elephants live in Asia and Africa.
work well like the distance. So that's all of the thing should change. So finally, I have to talk this really the important thing we have to discuss. It's a fabric evolution and its influence on the latency. So first, you can see there, when I don't use the fabric, consider fabric evolution, just read from the Falias Manzari 2004, and you can see there, it non-liquefaction at the stress ratio is equal, like that, okay? It's so liquefaction there, it's totally a different picture. So we have to consider the fabric. It has to move toward to zero effective stress point. So if it's not like this picture, it means it could not really model liquefaction in cyclic loading. So, but it's because it reaches stabilized point pre liquefaction. So we have to fix it. Dafalias and Mazari just use this formulation. We have this long V because it's 0, so this will be EVB, BVB 0, division K, and dilation C, the 8, so it's focused to D. So if you want to change DP, you have to change D, depend on D. So now for the next. How to change D? But we have to focus. When we modify D, we have to make sure that it's not affect to monotonic loading path and should not also affect on the untransgest path cycle earlier. Okay, so two things is that not affect to the other thing that we did earlier. And Davalet and Menzari 2004, they just realized they just have the paper articles know that a contact normal oriented distribution called fabric anisotropy during dilation phase formulation. So okay, fabric anisotropy generated during forward loading phase due to dilation. So it will not affect forward loading path. We modify D, it means we modify the AD. And we make sure the AD just only change upon reversal loading. And they propose the following law like that for this observation. AD is 0, 1 plus X yes, and where is all we have the Marquis bracket at Z at on positive or negative. That is a parameter control magnitude fabric on isotropy. So it's equal to Z or just 0. So we focus so only change upon reversal loading. Okay. And there, with this color like blue or magenta, okay, this color we have this, and this color we have this during the forward loading and reversal loading. We focus on Z is caused by dilation and link Z to negative volumetric plastic strain increment. So we have the finally formulation. dz equal this, okay? And here is all of the sign. We have the CZ, Z, SE, max, Z, like that. And we have this, so it's always make sure Z Z never exceeds Z max, because Z approach Z max and the Z reaches 0 and stop. So okay, here is the picture. So everything I just explained above maybe make you confused. So now I will use my animation and explain it carefully and slowly to make sure we understand it all. Here's the table from my presso, but I editing it to make sure all uppercase in my model. So when before I start, I want to show you this is the code and with the DZ and AD like that. Mm, okay, so with the DZ, you can see we have get all of the parameters. CZ, you can see over there is 600 in parameter controlling evolution of Z. We have update mockery like that. It's equal to when it's positive and it can use the value, and when it's equal to 0 or negative it's 0. Okay, return. So and this df long vp we have the controller is mean z, controller is mean z. Okay, is you can 1 or minus 1, and z max is for like it's called maximum value of fabric z, and the z is always change when the z change to make sure it. And finally we have the AD is E0, E0 is 0.704 called straight density C parameter AD. And we have update max calculate like that, and we can X and yes like that. Okay, so we focus to explain this now. Before I start, I should copy this figure. Okay, to explain it's easier because when I open the animation will stop and you can see anything in there. So that's why I have to use this over there. Let's do 2.5. Okay, I will lower and make it smaller. Okay, is it work? Is it work? Is he hard? Okay, wait me for a sec. 5 minutes, no, maybe 10. Okay, so now I will explain the model right now. It's hard, but okay. 3, 2, 1, go. So, I call it 7 stage, no, 9 stage. It means 9 line for load, unload, load, unload, load, unload, load, unload, load, unload, load, unload. So finally is there. So we have totally 9 time for load and load. Okay, and I explain all of the things fabric in this figure. All of the figure I just introduced from the beginning of the video, so now I just don't explain it again. And we start with the first figure. So okay, for the first figure we can call it loading forward or compression shear. Okay, for the first time you can see there we have df long vp is positive. So with this positive you can see to the dz when it's positive, and it will make dz is 0. So okay, and you can see 0 is mean 80 is A0, and you can look at this figure. This figure is 80 is not changed at all, and it's down. DSOVB is not negative because our loading stop when it not meet to our loading surface not meet the latency line. So we go to the next reversal loading. The next reversal loading we have under there, we have new latency line because of a loading, and you can see I did change the DF long VP. Now DF long VP is positive is really right. It's really true. It's not wrong at all. So we have df sum vb is positive at first. Df sum vb is positive, it means dz is 0. And this is 0, so z not change. You can see to this figure, z not change. And even AD is not changed because Z is 0. So AD is 0 and it's not mid dilatancy line. Next, for the third stage, we have the loading forward like that, and it still did not meet to the dilatancy line. So it's the same with the first stage. This is the third line, okay? And with dz equals 0, and so z is equal 0, and ad is equal a0 again. So we can see there z and ad did not change from the beginning at the time. So the fourth time, everything changed now. For the reversal loading, you can see first we have the vp is positive at the first time, but the VB will be negative when the loading surface meets the dilatancy line like that. So you can see there for the first time we have dz is called 0 because the VB is positive, and AD is still A0 and did not change. But when we go to the next is this will be when they change to negative, and we have dz is positive. Why positive? You can see this formulation, the dz and z like that. We have z max minus z max, and z is equal 0, and with equal 0 and z max, so minus z max, so we had the minus and a minus out there, so we had the positive dz, so it's make z positive. Okay, it can develop, but you can see z will become the z max because dz is positive, and just really equals z max, and this max dz is equal 0, so it's totally good. So we have the z increase in this stage. And when z inject, it means our z will change from the 0 to positive. So at that time we can still have AD equals A0 because x is minus 1. It makes it negative or equal 0. So the AD still not change. So you can see the red line did not change. And the next stage will be fun and everything will change now. So we have the fifth line like that. I call it fifth stage. At the time, we have the load forward. And the first, when the loading surface in the compaction, we have the some VB is positive, and when it's dilatance, and the some VB is negative, which is first time in negative in there. So let's go to explain. The first time when the some VB is positive, we have the DZ is all called 0y because the epsilon VB in this formulation is positive into DC is equal 0. But our Z is still positive because the previous stage. So that's why we have Z is positive. Positive and X is positive too. So we have the new AD. AD changed immediately like that from 0.704, it changed to 1.7227. Okay, it changed immediately from the line below to the line over there when we have in the compaction because Z is positive, and you can see that Z is didn't change at the first time. But okay, we go to the next stage of dilatance. Dilatance mean DSMVP is negative. So at the time it's negative, we have the disease is negative like this. Okay, and when it's negative, and we can see there the Z will reduce immediately, but it's changed like that. Z will from positive equals 0 and negative when it's positive. When it's positive, you can see there the AD will be okay. AD is still more than A0, but it's reduced to the A0 when it's negative and equal 0. So you can see when AD over there and it change to this and be A0 when our Z is negative and equal 0. So that's the second figure. So we have two of them like that. It's positive and it's lower equals 0. This is the fifth. And how about the sixth? A sixth stage is reversal loading. With the reversal loading, you can see there for the first time we had a compaction, and the next time we had a dilation. You can see the diaphragm VB now is positive when the compaction. So let's talk about that. In the first compaction, we have the diaphragm VB is positive, so it means DC is equal 0. Like this Z is equal 0, so Z didn't change when it's in compaction, so it's the horizontal line like that. This Z not change. This Z did not change at all. So Z did not change, but we have the Z is still negative because of previous stage. So that's why we have to use this formulation because C is negative and X is minus 1. So we have AD. So you can see when C is negative and did not change, we have new the AD. We had a new the AD over there. It's 2.772. Okay, change immediately from A0 to this A, new A, because Z is negative. But when we go to negative here, the next stage is dilatance. We have the epsilon VB is negative, and with this negative, we still have the new DZ is positive, and so this is will change. It's increase. So we have Z from when it's negative equals 0 and positive. So with that negative, the AD will reduce. You can see the AD when it in the air and it's reduced to the A0. And it stop when Z equals 0 and positive. It's make this formulation is negative, so that AD is equal to 0. So it increase and the AD is reduced like that. Okay, and this is the seventh stage. We nearly did it. Seventh stage is compaction and dilation again. It's completely look like the fifth stage. At the seventh stage, for the first time we still have the compaction and the next is dilation. With the compaction, we have the Z is called 0 like this. Because Z is still positive, so that's why we have the AD like this. When Z is positive, so it's over there. Okay, and when to the dilation, the epsilon VP is negative. It make DZ is negative too. So DZ just make Z from positive change to 0 and become negative. So when it's equals 0 and negative, it should make AD to A0. But when it's still positive, like this, and it's make AD reduce to the AD, A0. Okay? So we have this next stage. It's too complicated, but when we try to explain stage by stage, it's really easier. And for the A state, first time we still had a compaction, and the next time when mid dilation line and it become dilation. So for first, when compaction, we had direction VP is positive, so we have the dz is equal 0. The dz equals 0, and it means dz did not change at all. Dz did not change, but z is still negative. Z is negative, so it will make AD there negative and X is negative. We have the AD, this, we have this formulation. So you can see there, when it's Z did not change, we have the new of AD over there, okay? But when become dilation, Dilson VB is negative at that time, and we have the DZ is positive. So it will increase Z from negative equals 0 and become positive. When it's still negative, we still have AD equals A0 like that, 1 plus Z. So it will reduce to the A0. And when it's equals 0 and positive, we have the AD equals 0. And the Z is not there. Finally, we have 9 stage. It's 9. It's not a line because it curves, okay? We call it 9 stage. And with the 9 stage, we can see there is still compaction and dilation. So it's loading forward. When compaction, we have dz is equal 0. Dz equals 0, and you can see z is positive. Positive is mean AD. We use this formulation when it's positive, and AD equal A01. So you can see when it didn't change, you can see the AD is over there. Didn't change, oh, it over there. Didn't change, oh, the over there, okay? And when we come to the dilation, like that, when the loading surface meets the dilation line, and we have dz is equal to negative, dz is negative. So it makes our z move from positive to 0 and to negative. And at that time, when it's still positive, there, AD like this, and this when it equals 0, we have AD is 0. So you can see there, AD just reduced to the A0. So that's all of the thing I want to explain you with this loading forward and reversal. Hope all of you guys enjoy this video and it make you familiar to fabric effect of DZ and AD. From my word, it's from my professor, it just really look like the same. I just explain you 9 stage. This include all of them, okay? Just focus on this on VB is positive and this on CB is negative. It means compaction and dilation. There, notice Z and AD are not changed during the first several cycle, or positive Z might start to develop first. That's all I showed you from my animation. You can see there, when Z didn't change, AD and Z positive remain unchanged until the dilation phase occurs. Yeah, that's all I explained. That's how we understood mechanism of fabric and its respective development. So thank you, Dafalat Manzari Professor article 2004. Okay, I think it's enough for this video, just 45 minutes. And when you do the code, just focus on the side. It changed a lot when during reversal, so focus on that. I will try to take a look quick and explain to all of you. Okay, that is all. I have something to show. This is my from my professor Jenny. I see the loading step diagram, so that just make me an idea to make this figure. It just you can see there. It move from 0 over 0 reduce. It look like real. So that's why I change this picture. For the first time, you can see there. It's I just draw the axial strand and volumetric strand, but this is my final version, and I draw to the step and derivative strand. This make it look like real. Okay. Everything I want to know to you, I did. Now I want to explain more thing. Wait me for a sec. I'm trying to finding something else to talk with you. Okay. First, I want to make it clear, understand alpha and eta. So, this is a picture I want to draw the eta and alpha. You can see there the eta is this line, but the alpha is the zero line. So, this figure I just don't draw it, but you can see eta and alpha. Eta and alpha. Eta is always large, bigger than alpha. There, to 0.70, 0.34 and 0.33. You can see there at the first time in the loading forward we had eta above and alpha below. But when you see there, when we change to a load like that, we had alpha and eta. Alpha always bigger than eta. Alpha is always bigger than eta. Okay, so eta is smaller than alpha. Eta is bigger than alpha. So for the unload, we had alpha first, and the eta is below. To make it clear, I draw it on this load eta and alpha. When eta more than alpha, you can see the picture. I draw it more clearly. Alpha is above, and no. Eta is above and alpha is below for positive and negative case. The distance is m. M is just 0.1, so you can see it. So eta is bigger than alpha. And the next one is negative, and you can see there eta and alpha. Wait, it's a load. Okay, it's load, and now it's a load. Eta and alpha. That eta is smaller than alpha. It's above. Alpha is above eta. Okay, I draw the two pictures. So that should make it clear. One more thing I want to talk with alpha and eta. So you have to focus on there. We have two if. The eta and an alpha like that. But we can just use it to use the sign, change the sign in the absolute. We cannot change use the sign or use the controller like that. Eta and alpha is just on the use surface. But when you want to check loading reversal, you have to use different. You have to check the eta and alpha, because when we use the eta like that, you get the new alpha, and with the new alpha, this formulation will change. So make sure it's different if. But you can copy the sign to this. You can you don't need it when you use this and this. But you can do that, okay? When you want to do this, you can. It's will wrong. It's make your figure wrong, okay? Because this is the exactly loading reversal. Because I wanted to talk. And finally is MB. The MB and MD is not always taken to positive. Okay, it's a method distance. I taught you. You can change this to this code and it will work. The controller over there, like minus change to plus, but when I change the minus over there, it still work. But you have to change it all from this, this, and this. Focus on this DM down. It will be negative, so make sure DV and DB is negative too, and it's make it positive for the SMVP. Okay, there's a figure, something wrong there. That's it to make sure. That's everything. Hope all you guys enjoy this video and hope all you guys have a good day. It's just animation of Sandy Sand model that Falias Manager 2004. Thank you, my Professor Habui. My name is Tai Dinh Nguyen. I'm a PhD candidate and hope you guys have a nice day. We are in MCG lab. Welcome all you to Monash University. Chichi.